I'm doing a run through on tomorrow's activity. Carbon dioxide can make a solution acidic, and how your hot breath uh, can make something more acidic. And if you give me a second, I will share my screen, and we will be able to take a look at it. So hold on one sec, and we'll go through. Uh, do. There we go. All right. All right. So take a look. Um, okay. So let's see what we got. If you hear anything in the background, Sammy, he's hanging out with me. So we'll make do with what we got. All right. Uh, so let's take a look. Um, Carbon dioxide can make a solution acidic. Remote learning assignment lesson 610. This is the last one that we're going to use in the in this series because we're going to do a review on Wednesday and then assess on Thursday. And Friday's Halloween, so we're going to look at some Halloween stuff. Okay. So let's see what this is all about. Okay. In the previous lesson, you saw that acids and bases are like chemical opposites. You saw that a base can neutralize an acid and that an acid can neutralize a base. This lesson, you'll see that the carbon dioxide gas from different sources can make water acidic. You'll also explore how too much carbon dioxide in the ocean is causing a condition called ocean acidification. Uh, we'll look all the way down to the molecular level to better understand how carbon dioxide makes water acidic. Let's take a look. Now it's a blowing breath into a universal indicator solution. Let's watch it. So that implies that there is other gases in your exhaled breath. We exhale carbon dioxide, but the implication is that there are other gases as well. What do you observe about the color of the indicator solution when the person exhales into it? It went from green to a yellow orange. All right. Is it getting higher or lower? Well, it would get lower. Is the solution becoming more acidic or basic? It would become more acidic. And that should basically say yellow, green becomes more acidic and pH gets lower. Yes. All right. The air that we inhale is 78% nitrogen, 21% oxygen, less than 1% carbon dioxide, and some small amounts of other gases. We exhale the same amount of nitrogen, but the amount of carbon dioxide has gone up by 4%. The amount of oxygen goes down to about 15%, and the amount of water vapor increases. From this one experiment, it's not nearly possible to tell which of the gases in the exhaled breath is causing the color change in the indicator. We'll need to do another experiment to help figure it out. All right. and my kid is playing footsie with me. All right, testing how an indicator changes color with carbon dioxide gas. All right, so let's take a look. All right. So in this experiment, what was different about the air inside the cups with the carbonated water compared to the air inside the cups with the water? Contain more carbon dioxide. Since the indicator turned yellow inside the cup with carbonated water, what do you think caused the color change? CO2. Why do you think this? Because it was isolated in the carbonated water. Water. All right. Does the color change to the indicator solution become more acidic? Yep. Did it increase or decrease? It decreased. All right. And you can take a look at the, it was isolated in the carbon dioxide. Yeah. Carbonated water. All right. So video indicator changes colors from carbon dioxide gas produced in a chemical reaction. Let's take a look. All right. It's only a minute. That's an easy one. All right, in the experiment, what was the major difference from the air inside the cups with the vinegar and baking soda's reaction compared to the air inside the cups with just the vinegar? It had more carbon dioxide. Since the indicator became more acidic, how do you know it was carbon dioxide and that caused this acidity and not the molecules of vinegar that got into the air and then into the indicator? Um, Carbon dioxide um, reaction nullifies the vinegar, and the vinegar didn't react when the air, um, the vinegar by itself didn't react when the air touched it. The air with without carbon dioxide touched it. the experiment, only one variable was changed. The addition of baking soda reacted with the vinegar to form carbon dioxide gas and caused the indicator to become more acidic. It didn't change in the cup with only vinegar. This means that the vinegar did not cause the change in the other cup. Look at the chemical equation for the reaction between carbon dioxide and water that creates carbonic acid. So carbon dioxide, H2O, makes H2CO3. All right. So this is the water, or this is the carbon dioxide, and the hydrogen bumps off of the water and adheres to the carbon, the hydrocarbon, uh, a carbonic molecule. This is a carbonic molecule, right? And then this becomes the carbonic acid. It's kind of cool. So as the carbon dioxide gas reacts with the water to produce a substance called carbonic acid, the 2 hours in opposite direction means that this reaction easily goes back and forth with the reactions forming the products and the products coming apart into the reactants. Oh, that's kind of cool. It's considered a weak acid, but it can have a very big impact on the environment when there is too much of it in our oceans. How many atoms of hydrogen, carbon, and oxygen are in one molecule of carbonic acid? Uh, 2, 1, 3. 2 and 3. All right. Hydrogen, carbon, and oxygen, 2 and 3. Carboxyl, carbonic acid is a weak acid, and that is reiterated right there. And let's consider the problem of oceanic acidification. You probably heard that too much carbon dioxide in our atmosphere contributes to the problem of global warming. There's also another problem that exists that excess carbon dioxide causes. It's called ocean acidification. Ocean acidification happens when extra carbon dioxide goes into the ocean, reacts with water, and produces excess carbonic acid, which makes the oceans more acidic. The ocean isn't actually becoming an acid. Its pH is not getting below 7. The ocean's normal pH is about 8.2. The term ocean acidification means that the ocean is tending to become more acidic or less basic. It has moved from about 8.2 to 8.1. This may not seem like a big change, but it is a big change to organisms that live in the ocean, which are very sensitive to changes in pH. When ocean water becomes more acidic, it causes two main problems for the shell making organisms like clams, oysters, and coral. First, it becomes harder for these organisms to make their shells. Second, if the water becomes too acidic, existing shell can react with the more acidic water, causing it to break down. The ocean is a base with a pH just above 8. Extra carbon dioxide gas dissolves in the ocean, causing it to decrease, the pH to decrease and become more acidic by like 0.1. When the ocean pH drops, it's more difficult for sea life to produce shells, and the existing ones break down. And all that was but a bump. Why does it interfere with shells and shell making? Clams, oysters, and coral and other shell making organisms make their shells out of two ions, the calcium and the carbonate ion. Both of these ions are available in seawater. The organism takes in these ions, which join together to make calcium carbonate. Calcium carbonate is the main substance for the structure of the shell. But the extra carbon dioxide gas in the air forms extra carbonic acid in the water, and this causes a problem. It changes the carbonate ion, which shell making organisms need, into bicarbonate ion. The organisms can't use bicarbonate for shell making, so it goes H2CO3 plus hydrogen makes a carbonate ion, which is HCO3, and a bicarbonate, which is HCO3. Right? A proton from the carbonic acid bonds to the carbonate ion in ocean water and creates bicarbonate, which the shell-making organisms can't use. This means there are fewer carbonate ions for the creatures to attach a calcium ion to, making it harder for them to make the calcium carbonate they need to make their shells. Extra hydrogen ions in the water also make the water more acidic. If the water eventually gets too acidic, it might react with the calcium carbonate in the shells, causing them to break down. So, what ion do shell making carbonates, shell making organisms combine with calcium to build their shells? That's carbonate. When the pH drops, some carbonates gain a proton and turn it into bicarbonate, which they can't be used by organisms. Remember, if you don't want to listen to me read it, you could always fast forward when I'm reading this stuff. You could always fast forward during the videos. That's why these videos don't have to be as long as it says they are. Shell making shell makers combine calcium and carbonate to form shells. That's why it's called calcium carbonate. And the carbonate ions will take on protons and turn into bicarbonate, which cannot be used to build shells. All right. So we'll watch a video about ocean acidification. The narration action of the video go by pretty quickly, so you might want to stop the video in a few places to be sure you understand what is being presented. Let's review the topic before watching. There are a few screenshots from the video with explanations that might be helpful. The green dots represent excess carbon dioxide in the atmosphere due to the burning of fossil fuels. The ocean absorbs a large amount of this carbon dioxide. The little orange characters represent carbonate ions, which the shell making organisms need. That's cute. They use carbonate ions and calcium ions to make calcium carbonate to build their shells. Carbon dioxide, green circles, react with water and produce carbonic acid, green irregular blobs, which produce hydrogen ions. The pink circles, these ions bond to the carbonate ions and create a substance bicarbonate, not shown, that the organisms can't use. With shells difficult to make, clams and other shell-making organisms will be smaller and not reproduce as much as the creatures that eat them may not get enough food. This could affect the whole food chain. And the extra hydrogen ions don't just bond to the carbonate ion, they also make the water more acidic. The oceans become so acidic in the future that the calcium carbonate shells could react with the water and break down. Now let's watch the video. acespace.org. Ace Science Shorts. I'm going to take a look at those videos. Ace Science Shorts. Science Shorts. I'm writing it down. All right. It's actually a good thing in a way that the ocean absorbs carbon dioxide, but it's a bad way too. As far as global warming goes, why is the ocean absorbing CO2 a good thing? Less CO2 in the air means less global warming. All right. Or a lower rate of global warming, or a lower rate of global warming increases. As far as ocean acidification goes, why is ocean absorbing CO2 a bad thing? Because CO2 reacts with CO2, not zero, CO2 reacts with seawater to release hydrogen atoms that bond with carbonate ions that no longer can be eaten by shell making animals, organisms. All right. In the ocean, carbon dioxide and water combine to form carbonic acid. Um, uh, why is carbonic acid bad for shell-making organisms? Reduces the amount of calcium ions in the world. It turns carbonate ions into bicarbonates. Yes. And that basically says all that right there, which is good. And that's it. So I like this one. It was seemed like a good one. I had to read a little bit more, but in reading more, it took a little bit more time. So the video might be longer in that regard. But without reading it out loud and reading it in your head or like skim reading it, you can get this done relatively fast. So this is cool. Um, let's see. This is for Tuesday. So Wednesday we're going to be reviewing. Thursday we're going to be assessing, and then we're going to be done with acids and chemical reactions. So peace and hair grease. Take care, guys.